This is a video for MEI Core Pure Mathematics, complex number 6 exponential form, 6.2 using the exponential form of a complex number. Start with two quick examples. I want to write this complex number in exponential form, so for that I need its modulus, which is 4, and I need its argument, which is pi by 4, and I'm going to get that z is equal to 4 e to the I pi by 4. For this complex number, which is in x plus iy form, well, I need to look first of all at a quick Argand diagram so I can sort out where that is, and this is going to be minus 2 2i. This angle here is pi by 4, so this angle here, which is its argument, is 3 pi by 4, and then for its modulus it's just the length of the diagonal of a square of side 2, so it's just 2 root 2. So this is just equal to 2 root 2 e to the I 3 pi by 4. And notice I've split the I and the argument apart, and sometimes I might even put brackets around it to just bundle the argument up. There's that written up neatly, modulus, argument, and again here modulus and argument. So let's have a look at 4 plus 4i in exponential form. Start with an Argand diagram. There's 4 plus 4i, 4i. This angle I think we can see straight away is going to be pi by 4, and this length here is the diagonal of a square again, so it's just going to be 4 root 2. So 4 plus 4i is equal to 4 root 2 e to the I pi by 4. And so if I try to solve z to the 5 is equal to 4 plus 4i, the best way of tackling that is to write z to the 5 is equal to 4 root 2 e to the I pi by 4. But remember, I can add multiples of 2 pi to the argument. So when I now take my fifth roots, z is equal to 4 root 2 to the power 1/5 e to the I 1/5 of pi by 4 plus 2k pi. So that's fifth root of the modulus, 1/5 of the argument. And that turns out to be root 2 e to the I pi by 20 plus 2k pi by 5. And that's for k values 0, 1, 2, 3, and 4. So plugging those k values in, I'm going to get when k equals 0 that z is equal to root 2 e to the I pi by 20. When k equals 1, I'm going to get that z is equal to root 2 e to the I. I'm actually going to get an extra 8 pi by 20, so this is going to be 9 pi by 20 here. And when k equals 2, again, it's going to be 8 pi by 20 further on, so z is going to be root 2 e to the I 17 pi by 20. When k equals 3, z is equal to root 2 e to the I 25 pi by 20. Again, 8 further on. This is out of range though, because I want theta to be between minus pi and pi. So I need to spin that back by 2 pi, and this is going to give me that z is equal to root 2 e to the I, and that's going to be minus 15 pi by 20. And when k equals 4, z is equal to root 2 e to the I 33 pi by 20. And again, that's too large, so I need to spin it back again. So that's going to be root 2 e to the I minus 7 pi by 20. Now a useful trick you can use is you can think about this one as being a k value of minus 2 and this one as being a k value of minus 1. So whether you use positive values for k, work them through and bring them back into range, or whether you use negative values for k is entirely up to you, but the required values we need are these 5 here, and there, there, and there. Okay, that's written up more neatly for you. There's our original modulus and argument form of 4 plus 4i. This is where it's been divided down to get the fifth root, and then this is working through each of the k values, and notice we need to bring them back into range for these two here. So in this final example, we've got a pair of brackets here. We've got z to the 4 minus e to the I theta and z to the 4 minus e to the minus I theta. Notice the extra minus sign, and it's equal to this expression here. So start with the two pairs of brackets. So z to the 4 minus e to the I theta times z to the 4 minus e to the minus I theta. When you multiply that through, you're going to get a z to the 8. You're going to get a z to the 4 e to the I theta and a minus z to the 4 e to the minus I theta. And then you're going to get plus 1 on the end because e to the I theta times e to the minus I theta just cancels out. If I look at what I've got in the middle here, I've got z to the 8 at the beginning, and then I've got a minus z to the 4 times e to the I theta is cos theta plus I sine theta, and e to the minus I theta is cos theta minus I sine theta, and I've got my plus 1 on the end. These two bits are going to go, leaving me with just z to the 8 minus 2z to the 4 cos theta plus 1 as required. Now I want to solve z to the 8 minus z to the 4 plus 1 equals 0. And if we look at that, these two things are very similar. So this is like solving z to the 8 minus 2z to the 4 cos theta plus 1 equals 0 when cos theta is equal to a half, or if you prefer, theta is equal to pi by 3. So we know this thing factorizes up here like this, and if theta is equal to pi by 3, then basically I'm solving this equation, z to the 4 minus e to the I pi by 3 times z to the 4 minus e to the minus I pi by 3 is equal to 0. Now from that, I know that one or other bracket must be 0, so we've either got z to the 4 is equal to e to the I pi by 3, or I've got z to the 4 is equal to e to the minus I pi by 3. And again, remember we can put on multiples of 2 pi. And so now, finding my fourth roots in both cases, I'm going to get that z is equal to e to the I pi by 12 plus 2k pi by 4, or z is equal to e to the minus I pi by 12 plus 2k pi by 4. And my k values can be 0, 1, 2, or 3. So you are just going to get z is equal to e to the I pi by 12, and that's plus or minus because I've got both bits here, or I'm going to get e to the I 7 pi by 12, and again that's plus or minus, or I'm going to get e to the I 11 pi by 12, and that one has had to be brought back into range, and again it's plus or minus. And finally we're going to get e to the I 5 pi by 12, and again plus or minus, and that one's been brought into range as well. There's that written up more easily for you. There's our first pair of brackets multiplied out to give us this solution. This is where we've identified that this thing that we're going to use is actually the same as that, but when cos theta is equal to a half, so theta is pi by 3. So we're solving that equation, which factorizes back to this with theta equals pi by 3, and that therefore gives me two sets of fourth roots, so I end up with plus or minus these things here. And if we look at our first pair of solutions, e to the plus or minus I pi by 12, that would be these two here. And the others occur in pairs in exactly the same way. The next video in this sequence is 6.3, expressing sine theta and cos theta in terms of complex numbers.